The topic of our project is Logitech wireless mouse. The presenters, me, Wong Ko Hua, Freddy Law, and also Nai Chen. So for our project, the existing parts of the wireless mouse is USB receiver, electronic box, roller, switch, bottom, cover, chassis, and also the mouse button. This picture shows the 3D modeling of the existing parts. So for the manual assembly process, we are carrying the assembly process with fixed layers and also sequences. The average time of our assembly process is 50.83 seconds. So for most of the parts in the original design, the possibility to be assembled using automation is high, except for the rollers, where the assembly for the roller is complicated and is hard to accomplish by a single robotic arm. Next. So for the redesign of components, the USB receiver have redesigned by extending the upper parts of the body, which is the parts in black shown in the pictures. For the bottom surface, as the USB receiver is redesigned, so the USB receiver holder has been enlarged and repositioned in the bottom surface. Besides, the bottom surface have addings of ribs and holder to hold the electrical box at its position. Besides, the screw holes is removed and additional clips is added on. For the cover, the binding patterns of the cover has been changed for the ease of assembling. Besides the switch, the dimension of the switch has been changed to fix the new dimension of the electrical box. Electrical box have slightly changed in dimension to fix into the bottom surface, while the roller has been designed to be symmetry to make it more easier in the to make it more easier in feeding process, so that the element can be recognized more easily. For the top surface, the chassis and the mouse button is combined into one single part, whereas in the inner parts, there is platform is added to fix the electrical box, as the assembling process were carried by assemble upside down, so an additional platform is required to hold the electrical box. In the design of fixture, the dimension is 120 times 70 mm, which is much more bigger than the mouse itself. So extra 5 mm protruding surface is set so that the robot arm is able to grip on the top surface when the top surface is inside the fixture. In the design of layer, all the parts is arranged in sequence so that the robot is more easier when to pick the parts, and the fixture is fixed at the 250 mm in front of the robot arm. Okay. Next, I will pass the presentation to Nathan.
Okay, here comes to my part of feeder design. So first of all, among all of my feeder design, I have chosen vibratory bowl feeder and also magazine feeder. The reason why I choose the magazine feeder for the electronic board is because electronic board is a kind of material which is very fragile. So yeah, that's why I choose magazine feeder for it. So here's I show some of my draw design in each of the parts. So first of all is the about the USB receiver design. So oops, sorry. How do I? Okay, never mind. Here at the first, how to say, at the first picture, it shows the, actually this is the second selection. This is the first selection. So as mentioned by Kok Hua just now, he actually helps me to redesign this part to make it non-symmetrical, which is having 1 mm of difference and 3 mm of difference over here. So with the height of 3 mm, it can perfectly fit into it and also differentiate the up and down position. I mean the orientation of it, of the USB receiver, so that it can move into the correct pathway. And the top blocking here is to prevent the USB receiver from vibrating too fast and run out of the desired pathway. So next is this one, it's roller feeder design. So as mentioned by Kok Hua just now, this uh, roller actually was redesigned to be symmetrical, so that we don't have to really how to say struggling on how to differentiate the top and I mean the left and right side and so on and so on. So as long as it is symmetrical, so first at here it will guide the roller move over here, and then there is a second selection at the left downside part. It will guide it into it, and then finally there is a top part blocking here from to prevent the roller from vibrating out from the track. So next, this is the feeder design for the top surface. The reason why it was used the hand drawing one, the reason is because it's quite hard to model out the really curved surface here. So at this in this part of the design of the feeder, I just shows the idea of how to make direct the parts goes into the desired orientation. So first of all, there is a guided pathway with the highest length over here. It can guide it to go into the how to say the pathway. If it is at the how to say left right is actually opposite to each other, it will not perfectly fit into there. So next, at the second selection stage, over here there is actually a pretty small how to say guideline as well. It will guide the things go inside. So why is it actually this part is actually designed to be until the halfway of the curve here. The reason why I do so is because if let's say I design it to be like fully guide it, when the orientation was wrong, it will stuck over there somewhere, something like that. So at the last picture shows that this is actually the last how to say the last selection part. It will guide through the things to move how to say there is the red part over here is actually having the enough space for the protruded part in the top surface here to be able to fit inside there. Okay, so here comes the feeder design for the bottom cover. So basically the first selection stage at the first picture, it will guide the bottom part goes into there, and then the second selection stage will be here. Since the I didn't show here, but anyway, you can actually referring to the to the bottom cover part. It's actually one left and right. For the left and right part, they are not symmetrical, so this part will help to push it out. And then here lastly is still the same with the previous one. There is a top blocking mechanism to provide a better guidance for the parts to move in the desired pathway. Okay, so here comes to the feeder design for electronic board. So before I talking about my design for electronic board, which is the feeder design, which is magazine feeder, actually I have asked my teammates who is Freddy. He helps me to he provides me with the dimension of the gripper so that I can make it like this one, 30 mm of length and 36.3 mm of width, so that I can make it, how to say, it can fit into the magazine feeder and catch the electronic board easily. And here comes to the robotic cell safety system design. Here, oops, sorry. There are actually 3 emergency buttons in zone 2, and zone 1 is the one that anybody can access. Zone 2 is only for the programmer and the service people. Zone 3, no one can access unless the robot is stopped. And emergency button is for emergency case, and control station here is just for the programmer and so on to control the stuff. And here, chains and guard posts are used in the first boundary here, between the zone 1 and zone 2, to alert the people who comes near to the robot area. And the wire mesh fencing are implemented between zone 3 and zone 2 over here to prevent anyone from accessing into the zone 3. And then for the economical justification, it was calculated that the payback period is actually 0.0445 years only, and the return of investment is actually 2,230.5%. So yeah, we can be rich soon. So now I will pass my presentation to Freddy.
Thank you, Nigel. My part will cover gripper design, selection of robotic arm, and cycle time analysis. For the gripper design, there are 2 major considerations that are taken. The first one is the stroke per joule. The second one is the workpiece weight. And the grippers being selected is the SC Hung EGI 080. This is the model name. It has a 57.5 millimeter stroke per joule, which is capable to capture all of our components, and 0.5 kilogram of recommended workpiece weight. For the gripper design, the design works basically is done on the gripper finger, and the gripper finger is designed using the SolidWorks, and modeling is done. Move into the selection of robotic arm. There are 3 criteria that we use to choose the robotic arm. The first is the gripper and workpiece weight. Second is the maximum reach, and the third one is price. For our case, our workpiece weight and gripper weight combined to have a 2.7 kg load. And when I entered this information into the ABB robot selector, it gives me 2 suggestions. One is IRB 1001. Second one is IRB 102. The first one has a 4 kg payload and multiple choice of maximum reach, which is 0.475 meter and 0.58 meter. And the second one has a 3 kg payload and 0.58 meter. The robotic arm being chosen is IRB 120 because of its low payload and have a same maximum reach as IRB 1001. And the price of IRB 102 is much lower than the first robotic arm. About the cycle time analysis, I modeled the picking and placing of the robotic arm in the SolidWorks as shown in the figures on the right. And the datasheet for the gripper and robotic arm is used to find the velocity of the rotation and the closing and opening of the gripper. And the total cycle time is calculated using the angle stated in the figures and the velocity from the datasheet. And the final estimated cycle time for this design is approximately 12 seconds, which is quite low. And when compared to the manual assembly time, we reduced the time by 76%. And that's all from me. Thank you.